This is Module 7.1. Module 7 deals with data analysis, so we're going to work into some probability. Now, let me warn you, I'm not very good at probability. I can handle the stuff for this class, but if you're planning on being a math teacher, you get so far in mathematics and they say take this class and this class and this whole bunch of classes. And then they'll give you a list of 5 classes and say take 3 of these. They'll give you a list of 4 classes and they say take 2 of these. And you get to choose which ones you want. I avoided the class called combinatorics, which is all about probability because I'm terrible at it. So when I make mistakes, it's okay to laugh. Just know I'm an ugly crier. All right. Gina must choose a shirt and a pair of pants for today's outfit. She has 2 shirts and 4 pairs of pants to choose from. How many different outfits can she make? So let's say she has shirts A and B, and she has pants 1, 2, 3, and 4. So what is one option for coming to school or wherever she's going? A1. A1. This sounds like a lot of trouble choosing what to wear. My system is really easy. Whatever pair of pants is on the bottom of the stack, that's the one that I wear. Whatever shirt is farthest on the left, that's the one that I wear. When they get washed, they get put on the right. So I do have to make one really difficult choice every morning. Do I want to wear a long sleeve shirt or a short sleeve shirt? And sometimes that decision is just too tough to make. So anyway. What is another option? A2. Okay. And then A3 and A4. That is every possible way to wear that particular shirt, shirt A. What would be another option? B1, B2, B3, and B4. Okay. What about 1A? But it's different. A1 and 1A are written differently. Why is it the same thing? Order doesn't matter. Doesn't matter if you pick your pants first and your shirt second, or you pick your shirt first and your pants second. No, it's the same outfit. So in this case, order doesn't matter. And when I say order doesn't matter, this is what I mean. A1 is equivalent to 1A. Can you think of a situation where A1 and 1A are 2 different options? When would A1 and 1A be different options? Oh, okay. So what if we're choosing the valedictorian and salutatorian of Emory High? Is A1 different than 1A? Not for most people, but for those 2 it is, right? If person A is the valedictorian and person 1 is the salutatorian, that is different than person 1 being the valedictorian and person A being the salutatorian. Okay. Also, like license plates. If my license plate said A1 and your license plate said 1A, are those the same? Are those counted as the same license plates? No, because order does matter. So when we say order does matter, this is what we're talking about. And both of those are going to show up in this chapter, this module. Okay? So the question asks, how many outfits are there? I simply count them. 1, 2, 3, 4, 5, 6, 7, 8. Okay? All right. Determining a sample space. A number cube, I love this. When I was a kid, this is so funny. This isn't going to make any sense to you guys. When I was a kid, and I was in elementary school, and maybe a little earlier than that, there was this push by, I don't know, some very prudish people who thought we cannot allow cards and dice in schools because they're evil. Yeah. Cards and dice are evil. And so because of that, in probability class, we no longer roll dice because dice are evil. Dice are gambling. We roll number cubes. I know, it's frustrating. Did you get it wrong? I'm sorry. Yeah, essentially. So whenever you see a number cube, that just means a dice. And I refuse to call a single dice a die. I just refuse. It's just like deer. What do you call one number cube? A dice. What do you call two number cubes? Dice. So I'm holding out on that one. Okay. So a dice with faces labeled 1 through 6 is rolled once. The number rolled will be recorded as the outcome. What is the sample space? So it wants us to list all possible outcomes. Well, this is pretty easy. It's just 1, 2, 3, 4, 5, 6. And anytime we want to present an answer mathematically that involves a list of numbers, we have a special set of parentheses to do that. It's those. So those symbols mean you're about to look at a set of numbers. Okay? All right. Then give all of the outcomes for the event of rolling 1, 3, or 4. If there is more than one element in the set, separate them with commas. Really? It just wants us to write 1, 3, or 4? I think that's all it's saying. Let me double check. That seems dumb. Okay. It just wants you to do 1, 3, or 4. See if this one's any different. Okay. So the sample set here, again, is going to be 1, 2, 3, 4, and 5. Give every example that is either a 2 or a 4. So that would just be a 2 or a 4. All right. All right. Interpreting a tree diagram. So suppose you are making a pizza. Okay? And you have 4 options for crust: thin, regular, stuffed, and pan. You have 3 options for toppings: mushroom, pepperoni, sausage. What are the possible outcomes? Well, here are all of my crusts. So I take all possibilities and I break them into a thin crust, a regular crust, a stuffed crust, and a pan crust. And then I take those crusts and I'm allowed 1 topping on each pizza. So I could do mushrooms or pepperoni or sausage. So what are the outcomes? I could have a thin mushroom pizza, a thin pepperoni pizza, a thin sausage pizza, regular mushroom, on and on and on. That is called a tree diagram. Doesn't really look like a tree, right? So if we went back to our original problem where we had shirts A and B, and we had pants 1, 2, 3, and 4, what would the tree diagram be? Well, if I started with pants, I could have pants or shirts. I keep doing that. I have the option of shirt A or shirt B. And then shirt A could be paired with pants 1, 2, 3, or 4. And B could be paired with 1, 2, 3, or 4. So what are the outcomes? Well, I follow this line and I get A1. I follow this line and I get A2. This line would be A3. This line would be A4, and so on. So this kind of looks like the roots of a tree. That's why they call them tree diagrams. So these questions say, how many outcomes are there? Well, I just count the ends. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many outcomes have thin or stuffed crust? So I need all of the thin crust answers or all of the stuffed crust answers. So I have 3 thin and I have 3 stuffed. What should I do with those numbers? Should we add them, subtract them, multiply them, divide them? Well, it wants to know, how many ways are there to be here or here? So if it is a thin crust, you win. If it is a stuffed crust, you win. There are 6 ways to do that. What if I said, how many ways are there to order a single pizza and get a thin crust and a stuffed crust? How many of our outcomes, how many of these include thin crust and stuffed crust? None. Okay. What if I said, how many ways are there to have a regular crust that contains sausage? So that would be thin crust and sausage. There's only one way to do that. Right? Do you kind of understand the difference between and or? Okay, we'll get more into that as we dig deeper. How many outcomes have both pans, crust, and mushrooms? So I look at all the pans. How many of those have mushrooms? Just one. Okay. For the dinner special at a restaurant, the customers must choose an appetizer, an entree, a side dish, and a dessert. Here are the items to choose from. We have 4 appetizers, 3 entrees, 2 side dishes, and 4 desserts. How many dinner specials are possible? Okay. So we build our appetizers. So here are all possibilities. Our appetizers are split 4 ways. Cheese, onion rings, chicken, and shrimp. All right. And then this appetizer could be linked with 3 entrees. Pot roast, grilled chicken, or lamb. Okay. And then the pot roast can be linked with 3 side dishes. Vegetables, corn, or potato. And the vegetables can be linked with 4 desserts. Brownies, cheesecake, pie, and ice cream. Who wants to fill that out? I don't. That's a lot, right? Okay. So how do we figure this out if I don't want to go through and count them all? Any ideas? How do we multiply them? Okay, so let's start with the appetizers. So we have 4 appetizers, right? How many ways can each appetizer be split? So my cheese sticks are split 3 ways. How many ways will the onion rings be split? 3. How many ways will the chicken strips be split? 3. And the shrimp could also be split 3 ways. So I have 4 appetizers that can be split 3 ways among all of the entrees. Okay? And then how much can each entree be split into? Well, I have 4 of these, and 3 of these, and 3 of these, and 4 of those. So this entree gets split 3 ways. This entree gets split 3 ways. This entree gets split 3 ways. So I multiply by 3. And then when I get down to the last row, this is split 4 ways. This is split 4 ways. So we multiply by 4. This is called the counting principle. Each appetizer can be split 3 ways among the entrees. Each entree can be split 3 ways among the side dishes, and each side dish can be split 4 ways among the desserts. So the answer is just 4 times 3 times 3 times 4, which is 144. All right. Okay, we're back into sample space. A box has 4 cards numbered 1, 2, 3, and 4. Rachel will toss a coin once and record the toss as H or T, heads or tails. Then she will randomly pick a card from the box and record the number chosen. Give the sample space, describing all possible outcomes. So first, she flips a coin. What can happen when she flips a coin? She either gets H or T. After flipping the coin, she will reach into the box and pull out a card and record its number. So there are 4 cards, 1, 2, 3, and 4. 1, 2, 3, and 4. So what is my sample space? I guess Rachel's sample space. H1, H2, and so on. So H1, H2, H3, H4, T1, T2, T3, and T4. Now, list every one of those that includes a heads. So that would just be H1, H2, H3, and H4. What if I said, tell me every one that contains a 3? That would be H3 and T3. Okay, last one. A toy company is going to issue new ID codes to its employer. Each code will have 1 letter followed by 5 digits. The digits 2 and 6 will not be used. So there are 26 letters and 8 digits. Assume the digits can be repeated. How many ID codes can be generated? Okay. So we're going to split into 26 letters. So let's start with the letter A. Okay. And then A can be split into 8 digits. 0, 1, 2, 3. Wait. Which one did it say? No 2 and no 6. So 0, 1, skip the 2, 3, 4, 5, skip the 6, 7, 8, 9. So this is my letter. This is my first number. This is my second number. 0, 1, 2, nope, 0, 1, 3, 4, 5, 6, 7, nope, no 6, 7, 8, 9. My third letter, I'm going to split that. 0, 1, 3, 4, 5, 7, 8, 9, and so on. So, how many options are there for my letter? 26. How many options are there for number 1? 8. How many options are there for number 2? And this can be a little bit tricky. If I pick B3, can I put a 3 there? Can an ID code contain 2 3s? Yes, it can. So this is going to be 8. Okay. What if I were drawing numbers out of a box and not putting them back in? So I reach in and I pull out a 3. There were 8 options there. When I reach in to pull out the next number, how many cards are left in the box? 7. So not only do you have to pay attention to, does order matter? You also need to pay attention to, are you allowed to duplicate the same number or letter more than once? So, so 5 digits, 8, 8, 8. 26 times 8 times 8 times 8 times 8 times 8. 8 to the 5th, which is a really big number. 851,968. Okay. Good luck.